Hello, my name is Louis Taylor. I study mechanical engineering at the University of Kent, and this is my flexion of the elbow presentation for biomaterials. So this presentation explores the specific flexion of the elbow article, which is found in the book Introductory Biomechanics. This is written by Ross Evia and Greg Simmons, and it's produced as a piece of work for the University of Toronto in Canada. So I'll discuss the background and objectives of the article and then proceed to delve into the technical aspects and relate the content found in the book to my own studies and provide a final discussion and give my opinions on the article overall. So the background of the article, as already mentioned, it was produced for the University of Toronto in Canada. It analyzes the stress placed on bones in the forearm as a result of elbow flexion and considers joint reaction forces. It concentrates primarily on the radius and ulnar bones, which are the two main bones in the forearm, and it draws relations to beam theory and looks at compressive and tensile stresses. So the objectives of this article, the main objective of the article was to estimate stresses in the forearm caused by holding weight W in place opposing gravity in the center of the palm. It will estimate the stress in the two main bones in the forearm, as already mentioned prior, the radius and the ulnar. And it will estimate the reaction force at the joint as well, which is the elbow. And it will consider stress distribution between bones, joints, and muscles and connective tissue. So the technical aspects of the article. So these are the assumptions we've made for this scenario. So as human anatomy is very complex regarding calculating stresses, various assumptions were made. So we've got the radius in length from the weight is 24 centimeters. The humerus is 32 centimeters, and the weight acts through a line corresponding with middle of the palm. The second assumption we've made is the hand and wrist treated as a rigid assembly. The third assumption is that we have a fixed axis of rotation, because during practice this axis of rotation isn't necessarily fixed, but for the simplification of this so we can calculate it, we're considering it as fixed. We've got the muscles exert the same force as each other, which again is not necessarily how it works in practice, but it's been done to simplify the analysis process. The fifth assumption, we're treating the elbow as a simple hinge joint with reaction forces acting through the center of rotation. And the sixth assumption is the forearm is in supination, which is basically meaning that the palm faces upwards. So these are the calculations and the theory. So the muscles engaged in the arm, we got the biceps, the brachialis, brachioradialis, and the ECRL, which are all found on the previous slide. The PCSA, which is the physiological cross-sectional area, this is an indirect measure of the muscle's force generating capacity. We have F equals 20 newtons per centimeter squared, where F is the force generated per unit PCSA of muscle. Assuming the quantity is the same for all muscles and taking W as 120.1 newton, which is that weight we talked about before in the center of the palm, and the net moment calculated was 37.2 newton meters. Now all these calculations, the equations will be mentioned in the next slide. So the joint reaction forces next. So we have joint reaction force in the Y direction, we have 377.6 newtons, and then in the X direction 304.3 newtons. This is 3 times greater than the supported weight, and this is typical of most joints when muscles are working at a mechanical disadvantage, which is where we've got this weight held out quite a distance in front of the body. So the max stress in the radius was calculated to be 46 megapascals, and the yield stress of the bone found in the radius is approximately 130 megapascals tensile and 200 megapascals compressive, which means the max stress produced from this scenario is within 23 to 35% of the yield stress. So it's obviously not near failure, but it's quite a large amount of stress on the bones, which is to be expected because they're working at a mechanical disadvantage. So and then we got a peak surface strain of 2,700 microstrain was obtained in correspondence with Young's modulus for longitudinal loading, which is 17 gigapascals, and the values for peak surface strain are typically around 2,000 to 3,000, so 2,700 is an expected value. So these are the equations used. We've got equation 8.15 from the text, and this was used to calculate F. So we rearranged this equation to make F the subject, and that's how we calculated F. We then got 8.16, which is the joint reaction force equation, and that's how we computed the value 377.6 newtons. And then we have the max stress in the radius, x and y direction, and this equation required multiple breakdowns of a simpler equation for it to be applicable to our practice. So this is the equation 8.24 breakdown. So we start off with 8.17, and we can neglect Fx in this equation as the axial forces have little effect on overall stress. So we rewrote this as these two equations. And this is for the radius and this for the ulna, so it's the same equation, but they're for each specific bone. And it's plausible that the ulna and radius are sized so maximum stresses are equally distributed upon these two bones. So we can rewrite that as these being equal to each other. And then using the fact that max y occurs at d over 2, we can now write 8.22 as this equation, and then where bending moment is maximum, ulna has approximately the same diameter as the radius, so this allows us to assume moments of inertia are the same. So we can now set the brackets in the denominator to 1 because we have the moment of inertia here and here is going to be 1, so it implies the bending moment in radius is half of that of the forearm, and because we have 1 plus 1 is 2, so it's going to be half of this, so we can just write that this is now equal to this, and that's how we get equation 8.24. So relation to my studies, we got lecture 1, we have stress and strain, Young's modulus, Hooke's law, Poisson's ratio. Lecture 3, theory of bending beams, distributed loads, bending moments. Lecture 4, stress and strain in beams, the stress-moment relationship, bending moment due to stress, bending stress, calculation of inertia. So the key relations, we have Poisson's ratio, which is the lateral strain over the axial strain, and we have the equations here. And this applies when looking at the stress induced by each of the forearm bones. We have distributed loads, which applies when exploring how load acts on the forearm, so it's distributed all along the bone. We have external supports of beams, which applies when exploring the role of the elbow as a hinge joint, so we can imagine this is the elbow. We have shear forces and bending moments diagrams, so there's bending moments on the forearm. Support reactions and theory of equilibrium. This applies when comprehending and calculating joint reaction forces, because we have to calculate what is the reaction at the elbow based on the applied moments. And then we got bending stress, which applies when looking at maximum stresses and stress caused by bending in the radius and ulna, and we have this as moment over inertia. So my objective criticism of this article, The analysis was oversimplified in some places, which was good for making it digestible for the reader, but it decreased the result accuracy. The results obtained for the most part lied within expected ranges, but are not reliable enough to use as close to true value. Assumptions were necessary for this sort of analysis, but again decreased the result reliability. And neglecting the variation in muscle length due to elbow flexion angle was required, but didn't give a good representation of the bending stress in practice. So a possible improvement to this article would be to consider all the muscles individually and calculate their own individual PCSA. Although the process would be much more long-winded, the results obtained would be far more reliable. Extra consideration given to how the joint angle affects the muscle length would have further increased result reliability. Acknowledging the force transmitted by the interosseous membrane, which is the connective tissue in the forearm, would have altered the stress values obtained for the radius and ulna slightly, as it would have induced some of that stress which would have been in the bones for this example. And maybe a possible software simulation on Abacus, which lets you analyze all the stresses present, would have been a good improvement. So to conclude, the article was clearly structured and presented the steps of analysis well. Analysis, although incomplete, returned plausible values which lied within the expected ranges. It presented a good number of diagrams, making it easier for the reader to digest the information and have better comprehension of what's going on. And a more complete conclusion would have made the article a lot better. So thanks for listening to my presentation.